Hey guys, I was given this Calibre 35 watt LED work lamp by Supercheap. They want us to review it, so we said yeah, we can review it on the provision that we do an honest review. We're going to tear it apart, see how it performs, and we're going to report on the good and the bad. They said yep, go for it. They want an honest review, so we're not going to sugarcoat this. If it's a good lamp, we're going to tell you it's a good lamp. If it's bad, we're going to tell you it's rubbish. So let's tear this apart and see how it performs. So we'll pull the thing out of the box, just a standard cardboard box, nothing too interesting. I will talk about the specs in a sec, and this is what we've got inside. So we got 7 LEDs there. Looks like some stainless steel hardware. That's pretty nice. Some nylock nuts. Feels like a soft, actually feels like a silicon lead there. 200 degrees rated, 2 by 0.75mm square conductors. So nothing terrible there. That's pretty good stuff. It'll be a powder coated case on that, powder coated black. So it should be durable. We'll give that a test as well. And what else we got here? What's this one? A warranty card. Don't need that. And in our bag we've got some more nuts and bolts to bolt it to whatever you're gonna fix this thing to. If I can get the thing open. So I got a rubber pad. That's gonna stop this thing from scratching when you bolt it down to your, to your chassis or to your front bar or whatever. That's a nice little touch. And some stainless steel screws. Once again, nylock, stop it from vibrating loose. So it looked like, what's that, M8s or something. Standard stuff there. So on the box, we've got the specs here. We got 7 high power 5 watt LEDs, you can count them there, for a total of 35 watts. It's a multi-voltage from 10 to 30 volts, so we'll test that out. The current draw, 2.22 amps at 12 volts and 1.18 amps at 24 volts. That's another test we'll do. It's a flood pattern, so it's not a beam, it's more of a wide dispersion. Good for lighting up a work area or something, hence the term work lamp rather than spotlight. It's white. It doesn't give us a color temperature. The lifetime says it's 10,000 to 120,000 hours, so pretty wide range, but 10,000 hours at a minimum is pretty good. I'm not going to sit here and leave it turned on for that long, so I'll take them at their word. Intensity, oh here we go, we've got intensity. Hasn't got color temperature. We got at 35 watts, it's 2,500 lumens, so we'll do some measurements of that. And the working temperature is -45 to 85 degrees, so that's a pretty wide range anyway. So let's have a bit of a closer look at this. So it's a cast, it feels like a cast aluminium housing with the plastic, that'll be a polycarbonate or a Lexan or something like that cover, and it's probably been glued in. I can't see any external screws. We've just got like a gland there, that's where the cable comes through. They're generally IP65 rated, so that's a nice addition there to stop the water getting in. That technically means that this is probably fully immersible. Actually, I wonder if there is an IP rating on this box. It doesn't actually say anything about the IP. That could be something they could add. Yeah, there's no IP ratings. But it would be nice to have that rating on there, maybe in a future revision. Alright, so first we'll test the voltage and current. So I'll turn that on. We got voltage here and current here. 11.69 volts and 2.5 amps. I've got it just face down so it doesn't blow out the camera with the bright light, because it is very bright. So according to our specs here, 2.22 amp at 12 volt. So we're a little bit below 12 volts, so we're going to have a higher current. If you notice there, as we go to the 24 volts, our current is lower. So at lower voltage, our current is higher. Because we're at constant wattage, that means it's like a seesaw. The wattage is like a seesaw, and as the voltage, like my fingers, goes down, the current goes up. As the voltage comes up, the current goes down. The wattage is always a constant. Alright, so we're getting 24 volts coming in, and basically 1.2 amps being drawn by the light. So You can see the lights working alright there. It's only mildly warm, it's all looking pretty good. And the specs, they are 24 volts, 1.18 amps. So we're spot on. It's good enough. The specs are good on this box, so I'm going to give that one a thumbs up. Now, I want to measure the colour temperature, see what that is. That's a calibrated neutral grey, so I'll put that under the camera and I can do the white balance calibration in the camera, and that will tell me exactly what the colour temperature is. Alright, so I've got the white balance card here, just sloping down towards the light, which is just off the screen there. It looks a bit blue now because it's actually set, the camera is actually set to the 4400 Kelvin, which is the lighting in this room. So I'll go ahead and recalibrate that to this light here, and we'll see what it comes up at. I can't actually show it on screen, the number or anything, because it's in the camera itself. So I'll just report back and show you what it looks like once it's been calibrated. And this is what it looks like when it's been calibrated. So this is 7000 Kelvin according to the camera, which is just above daylight. Daylight is considered about 6400 to 6500 Kelvin. So this is a little bit cooler, a little bit bluer than daylight, which is no problem. It's a nice white light. It's nice, seemed nice and clear. So this wouldn't be so good in foggy conditions, but then again, it's not a driving light. It's not a fog light. It's a work light. So 7000 Kelvin, nice and white. Oh, I'll give it another thumbs up, I reckon. Through the powers of Amazon Prime, we got ourselves a light level meter. Might do a tear down this later. It cost me about $15–20 delivered overnight. So anyway, we're going to use this to measure the output of this and compare it to what it says on here. So this here says 2500 lumens at 35 watts. This measures in lux, or I think candela maybe, but we'll be working in lux. Now lux is a point measurement, so when I measure, it's going to tell me what the intensity is right at that little white dot. That doesn't tell me how much total output, what it says on the box with lumen. We have to do a little bit of a calculation, so we have to measure how far from the light to the sensor. So a good ballpark figure is about 1 meter. Measure 1 meter back and make that your point. And also we need to tell the calculation the angle of spread, so we can not just take a point but the whole output across its whole range. So once we have those three figures, the output, the distance and the angle, then we can convert from lux to lumens and compare what it says on the box. So if I stick a piece of paper here and I'll turn this light on, so you can see the angle of spread. Now the manufacturer may use a slightly different angle, but we'll work on the main spread, the main lines here. So if we draw lines coming back and then measure that angle, that will give us a good idea of the angle of spread. So that's the first number we need. So if I grab my ruler and a pencil, something about like that, I think. Relatively close. And I get my tiny little cheap protractor. It's about 62 degrees or so. So we'll work with around 62 degrees. What I'll do is I'll run the calculation forward and backwards, so I can, once I get my reading from here, then I can work out the angle they used if we assume that their 2500 lumens is correct. We can then work the other way as well and use our angle to see what the output is. That way we can do a bit of a sanity check in both directions. Alright, so I'll get a tape measure now and I'll use this to see what sort of output we're getting. So we're looking at 1 meter. I can't quite fit the whole thing on the screen, but if you believe me that I'm standing back 1 meter. Alright, so our number is 592. It's actually a times 10, so we've got 5,920 lux. That's our output at 1 meter, our point samples. Alright, so I've done the calculations, went online to just an online calculator, and it's telling me that the output of this is a lot higher than what it says on the box. Now, the angle that you measure, this one here I measured about 58 degrees, and the first one I showed you, it was 62 degrees, so we're about, let's say 60 degrees. That's pretty much what I put into the calculation, and we come up to around about 5,000 lumens, which is a lot more than what the box says. The box says 2,500, so I've got double. But if I put the calculation backwards to work out what angle they use from my reading and all that sort of stuff, so that will come to a 43 degree beam angle. So it's 15 degrees less, or so, from like 58 to 43. So you're about 15 degrees there. So that angle makes a big difference, because as you're increasing the width, the amount of light you need to fill that gap is becoming a lot greater. So they may have used 43 degrees, they may have understated it, I'm not sure, but from my measurements it's definitely not giving out less light than what they say. It's a very bright light. So I'm going to give that a thumbs up. The light output is good. From my readings, we got 5,000 lumens on a beam width of about 60 degrees. According to their specs, it's 2,500 lumens, and that means they're using a beam width of about 43 degrees. So somewhere around that sort of range. But anyway, thumbs up, and next test. Alright, so I think the next step we're going to do is we're going to turn it on, put it underwater. Now that's not going to be much of a heavy test, because you've got a nice gland at the back here, and it's obviously designed to be waterproof. So yeah, so what? But what I'm going to do, just to do a bit of a harder test, is I'm going to turn the thing off and leave it underwater. The reason for that is it's easier to make something waterproof for a short term, but with electronic stuff like this, it warms up, so you get a bit of pressure inside as the air expands. Now when it's underwater, if there's water all around the seals and it cools down again, the negative pressure that occurs tends to suck the water past the seals, and that's why you get a little bit of foggy sort of water inside things that are otherwise waterproof. Because of that contraction after it's cooling down, sucks the water in, the vapor in. So we'll do that. I'll leave it on in a bucket of water, just sitting in there for a while, and after a few hours we'll turn it off, leave it there again for another few hours, maybe come back tomorrow morning or something, and then we'll see what we can, find if there's any water in there. Okay, got my nice bowl of Tokyo tap water, and we'll dunk that in there, completely submerged. So I've had this thing submerged in a bowl of water here for about 3 days now, turning it on and off, dunking it in and out, that sort of thing, just to see if we can get it to leak. And it looks like it's not leaking at all. So I'm going to go ahead and say that this thing is relatively waterproof. Thumbs up. I can't see any condensation inside at all, so there's no water getting in even after underwater. It's not like deep underwater, but it is fully submerged for 3 days, and turning it on and off to get the heat to make the air inside expand and contract and try and suck some water past the seals, but it just hasn't happened. So that's looking pretty good. Alright, next step is some mechanical tests. Let's see what happens when it starts getting bumped around a bit. Let's head outside and start kicking around in the dirt. Alright, we're outside. We'll give this thing a bit of a hard time. Jeez, can't even hold the thing. But just drop it on the ground. That's not going to really test the thing, is it? I mean, it's pretty solid as it is. But I had a bit of an idea. No, Mr. Bond, I expect you to die. So there's our light. You can see it's hit there where the mud is, still intact. And there's our crater. So it's all in one piece. Shall we do it again? Again! Alright, you crazy thing. One more time. You ready? Last one. Take that, you bar. Back down here again. That's where she lay. Where we hit this time. That's the old one. Well, there's a bit of a nick on the top there, on the side, sorry. Still intact.
That's where it hit there. That's a second hit. Right where the wire is too. That would have crimped that wire. Alright, where did it hit? Pretty much spot on the 1 and 2. Pretty much spot on the second from the first. Alright, let's take this inside, see if it works, and then we might crack it open. Alright, back inside. Let's see if this works still. Okay, let's connect it up. They're still working. Look at that. Perfect. All the LEDs, oof, that's really bright. All the LEDs are good. So, I think the next step is to crack this thing open and see what's inside. Now there's 2 ways I can crack it open. There's a boring way. I just leave this thing out because that's going to be elastic, or some Sikaflex or silicon holding that lens in and crack it open. Or we can throw it off the roof again. Throw it onto the road, eh? See if that cracks it open. Let's give it a go. High speed collision test number 3. Holy shit. Got a piece of plastic everywhere. Look at this. Little lenses. Look at that. It's just blown that out. But the actual thing is still in one piece. That's pretty tough aluminium. So as to be expected, our destructive testing was a success. Well, let's see if this thing still works, eh? Just plug it in. Wow, that's always so bright. Yep, we got all 7. I don't know if you can see in the video there. Yeah, all 7 LEDs are working at full brightness. So there's a big thumbs up there. It took 2 drops from the 3rd floor, that's the roof of the 2nd floor, into the garden, and it's pretty compact dirt, so it didn't just sink in. You saw that the crater wasn't so deep. So that's taken 2 good impacts, and then of course you throw it on the road from the same height, it's going to be really hard to make something not break. So the goal there of course was to break it open so you can have a look inside. But yeah, it seems pretty tough. It can take a good impact. It looks like here, that's where it's impacted the road. You can see the shiny bits along there. So it's hit the road like that, and that's bent this side in, and there's a bit of a crease. I can see a slight crack forming there, and that's what's pushed into the plastic, and that's just blown the plastic out. So of course almost no light is going to take that sort of impact, so that's not a negative on this thing at all. We tried to break it open and we did. So but dropping into the dirt from the 3rd floor, it could take that, no worries. So it does. I mean, there's a lot of aluminium there. It is very strong. So that's a definite thumbs up. So let's pull this thing out and we'll see what we can find here. Have a bit of a closer look, eh? Alright, so we just had 3 screws holding it in, and then we had the positive and negative wires just soldered to the circuit board there. Looks like there's a bit of white schmoo behind there, the heatsink paste. I'll get myself a flat screwdriver and we'll just pry this out. This should just kind of, there we go. Just have to unstick that white goop. Yeah, there you go. Nice amount of heatsink compound there to get a good thermal interface with the case. So here we are, zoomed in on the circuit board itself. White etch resist there. Looks like it's all surface mount. On the back, aluminium. Nice little design touch there. They use aluminium to get the heat from the LEDs through to the casing through that white goop. Usually a circuit board is made from fiberglass. You've probably seen, you know, this sort of thing, or this a lot. This is a fiberglass called FR4 board with the copper traces bonded to it. Then on top they got the solder mask there. So that's a standard circuit board, but these don't need to pass heat. This one does, so that's why they use the aluminium. Most LED circuit boards you'll find are actually stamped aluminium like this with a circuit board put on top. They'd use some sort of mylar between the aluminium and the actual traces, some sort of insulator anyway. So this board here, it's a Tough Plus brand, and the part number is F0201 H-35WV1. It's got here H equals 1.6 millimeters, so I'm going to say that that indicates how thick this thing is. Let's give it a quick measure. I'll get the old calipers out. .45. So 1.45 mil. So maybe that's like a total height including something. Anyway, so we got 7 LEDs, and looks like we've got 4 power supplies. So I'm not sure exactly how that's ordered. Maybe it's in pairs of 2, and then we've got a single. Kind of hard to see the traces under the white there, but we got maybe 1, 2, 3, 4, 5, 6, 7. Yeah. So the middle one is on its own power supply, and then these 2 at the top are on this one. These 2 are in a group here, and these 2 are in a group here. So we got basically little buck boost converters. It looks like we got like the flyback diodes, and we got a little controller, that U2 and where are we? U3, U4, and U1. They're a little controller chip. We'll have a close look at those in a sec. And we've got the characteristic inductors, inductor, flyback diodes, some capacitors. Got some, looks like power line caps maybe. They're probably across the positive and negative, just to aid in some smoothing, stop some noise getting out, possibly stop the switching noise getting back out into the electrics of the car. But yeah, it's pretty standard stuff, all surface mount of course. So let's have a look at these small chips, see what they are, and maybe get a data sheet. Right, I found the schematic. Actually pretty easy, came up straight away, so it must be a relatively common part. It's a PowerTech brand, PT4115, and it's a 30 volt 1.2 amp step down high brightness LED driver with 5000 to 1 dimming. So this chip can actually dim the LED, which is a nice feature. This product doesn't actually use that. So it says here it's a step down converter, so it's a buck converter designed for driving single or multiple series connected LEDs efficiently from a voltage source higher than the total LED chain voltage. So as long as your input voltage is higher than what is required for the LEDs, this can drive it because it's stepping down to suit the LEDs. It doesn't do any step up. It says over here, input voltage range from 6 to 30 volts. And what does our box say? Our box says 10 to 30 volts. So well within the range. So that's pretty much spot on. You could probably go a bit lower, but it depends on the actual topology of the circuit. But yeah, 10 to 30 volts. We're definitely not overdriving these chips or anything. So within their safe margins, no worries. And if we come down, we can actually see the schematic here. I'll zoom in on that a bit. Alright, so this is pretty much what we've got in each section of this circuit. This part here, we ignore that because that's for an AC input, so we've got a bridge rectifier to convert the AC into DC. We're running off DC from the car, so we don't have that there at all. Now this capacitor here is 100 microfarad. That's what these ones here are. We've got 2 of them, which are actually spread across for the whole lot, it looks like. No big deal. Maybe a little bit nicer if they had 4 of these, but the system works and it's not a big problem. It's just a smoothing cap really from the for the power supply. So you can get away with that in a DC environment because you've got DC coming in, you're not trying to smooth AC anyway. Then we come in and we've got a current sense resistor here. That will be one of, what would that be, R3 just here. I'll point it with a bit more pointy thing. That one there, and we got that one there, and that one there, and that one there. And what that does, that's a very low resistance, but it allows our chip to sense how much current is coming through the LED. You can see here, that's where the LED there is, 3 watt. And that lets this control it and not blow the LED by allowing too much current to flow. So that's our feedback. Just here, this little section here is our feedback circuit. We got here CSN, current sense. Then we come through the LED, or 2 LEDs in this case, some of them have got 2 LEDs, and through our inductor, that's those big things here. And this, along with the Schottky diode, this diode here and this inductor. That's what's doing our voltage conversion. So this is doing the main control. It's pulsing all of this, and it's using the inductor and the diode to drop the voltage down. And then we're coming out to the ground. And this one here, dim, that's where in the circuit we've got here, that one will be getting tied straight up to here. So that's always on. As soon as you apply power here and here, 12 volts plus 12 volts, and then 0 volts, that's the ground. We got 12 volts comes in, or whatever voltage, and then that turns the dimmer on, so the LED comes on straight away. If we were to put a control circuit in here, we could actually dim these LEDs, but that's not in this function. Now, so here's a drawing of the actual part itself. We've got a exposed pad here. This is used for heat sinking, so that part there, that leg that's a bit of a funny shape, that will be connected straight to the die, the silicon inside, so that will be mounted on that pin, just like this circuit board is mounted on the aluminium. And that allows any heat that's built up in there, because this is doing switching and whatnot, so it's doing a bit of work, and the heat can come out through that pin into the aluminium circuit board and be gotten rid of. So the Calibre 35 watt LED work lamp from Supercheap. What do I reckon? Well, with a 2-year warranty, it's 2,500 lumens. We measured that and it's at least that, maybe more. We've got a nice thick aluminium heatsink. It's a good layout. The chips are running within their rated specifications. It's all looking pretty good there. Nothing dodgy or no bodge fixes or anything on that board. We've got a nice thick cast aluminium heatsink / enclosure. Polycarbonate. Looks like polycarbonate to me the way it's shattered. Lens. Dropping it into the dirt from the 3rd floor, not a problem. I mean, we dropped on the road, and definitely it's going to crack open. But we were trying to do that, so I'm not gonna give it any thumbs down for cracking open at that point. We got a nice gland there, high temperature silicon lead with nice thick wires, stainless steel hardware. We soaked it for 3 days, turning it on and off, not a problem. So I'm going to give this thing a thumbs up. You're looking for a good work lamp? This one's a decent contender. Check it out. We'll see you next time.